This is an RNZ podcast. Kia ora and a very big hello. This is Elemental. It's a podcast from RNZ in which the chemically savvy Professor Allan Blackman is taking us on an alphabetical journey through the chemical elements. We're doing it to mark 150 years since the periodic table was invented. I'm Alison Ballance and I'm a producer at RNZ. And I know enough about the way the world works to know that everything is fundamentally made of chemicals and that there is no such thing as chemical-free.
Amen to that, Alison. Well said. And I'm Allan Blackman from AUT, Auckland University of Technology. I'm a professor of chemistry.
Today on Elemental, we're up to, episode 5 already, Argon. So tell me all.
Well, argon, okay, it has the chemical symbol Ar and the atomic number of 18, and that puts it on the very right-hand side of the periodic table up near the top.
So we're talking right-hand side as in location, not as in political leanings. What does that name Argon mean?
Argon comes from the Greek word argos, which means idle.
And it's a gas, isn't it?
It is a gas, yep. And in fact, it's probably more common than you might expect. It might be something that maybe you haven't heard of, but 1% of every breath you take, as Sting might say, is in fact argon.
That's terrible.
I know.
Oh no, you've just put that song in my head. Thank you very much, not. So who discovered it was in the air that we breathe?
Oh gosh, that sounds like a song by the Hollies as well. 2 for 1. Sorry. Oh, God,
okay, that's enough bad music puns. Moving right along.
Right,
Argon.
Okay, Argon. So, back in 1785, one Henry Cavendish was interested in basically the composition of air. And what he found that there was this 1% remaining after he took all the oxygen and the nitrogen out of air. And he didn't know what that was. So after Cavendish made his discovery, it sort of lay dormant for over 100 years, in fact, until two chemists, Lord Rayleigh and William Ramsay, in 1894, managed to isolate and really identify argon, this unusual component of air. And this was kind of interesting because this discovery of argon necessitated a redrawing of the periodic table.
But I'm thinking back to our prequel, back at the beginning of Elemental. We talked about the genius of Mendeleev, he who published the periodic table first. And we talked about how he left holes on the periodic table for elements whose existence he predicted.
Absolutely correct, he did. He left those holes, and those holes were on the basis of chemical reactivity of elements that were known at the time, and he could sort of determine the chemical reactivity of unknown elements at that stage. However, argon and its chemical cousins, helium and krypton and xenon and radon, these things, they just don't react with anything. They are what we call chemically inert. They just sit there and you give them the most reactive compounds, elements or whatever to react with, and they'll just sit there and look at you. And for that reason, they have no reactivity, and therefore they didn't appear, I guess, on Mendeleev's radar. He didn't know they were there. And so what was required was a whole new column on Mendeleev's periodic table for these elements, which were then christened the noble gases, okay? Noble in the sense of being not chemically reactive.
So that goes back to when you said its name came from the Greek for idle. That makes sense. Now, I quite like the implications of nobility, just lying around, not doing anything. But what actually makes them inert? And is this useful or is it a useless feature?
It's actually a very useful feature, as we will see with both argon and all of the other elements in Group 18. What makes them inert? Well, that's a first-year lecture in itself, really. Very briefly, it's got to do with the number of electrons that each of these elements contain in the outermost shell of electrons that they have. And this magic number in this case is 8, and they are very happy with 8 electrons. They don't need any more, they don't want any fewer. So that being the basis of chemical reactivity, these 8 electron, or the octet rule as it's called in chemistry, they are very, very happy as they are. And you might think, well, what are we going to do with things that are chemically unreactive? Well, for example, incandescent light bulbs. Way back in last century when they were a thing, you need the atmosphere inside the bulb to be chemically inert because you want the tungsten filament not to react with anything, and it's very, very high temperature, and so therefore it will react with most things. It doesn't react with these noble gases. If you want, for example, an inert atmosphere to do things like arc welding, again, you're at very, very high temperatures, so that makes metals very reactive. You can use argon in order to keep all of the oxygen and everything away from that. You can use it in double glazing. It's, again, chemically unreactive and not very conductive towards heat. And also food storage. You know, you want to keep oxygen out of things. You want something that's chemically unreactive. You can just pump a inert gas in there. Argon being the best, of course, because it's the most abundant of the noble gases.
Where does it actually come from? How's it produced?
One method by which it's produced is radioactive decay, as are a lot of the elements on planet Earth. And it comes from radioactive decay of potassium isotope. And this is very, very useful because when a potassium isotope decays in a rock to give an argon isotope, what you find is the argon gets trapped in the rock. And if you can then measure the ratio of this potassium isotope to this argon isotope, and knowing how long it takes for the potassium to decay to the argon, you then have yourself a way of measuring the age of the rock and ergo, therefore, the age of the Earth. So this is a very, very useful method for dating rocks.
Well, for something that just likes lying around, it sounds really useful. It's like a good advertisement for sloth. What's your favourite use for argon?
Well, if money is absolutely no object, then you can fill up your car tyres with argon. This serves two purposes. First, apparently it lowers the road noise, and secondly, it does protect the inside of the tyre from oxygen, which causes oxidation and degradation of the rubber. So that's a little bit ridiculous, but apparently it is done.
Sounds good. I've got so much money I pump up my tyres with a noble gas. But surely that just makes your tyres more expensive. I think I'll stick to pumping up my tyres with ordinary air tanks. It's free at the local service station. Just another handy hint from Elemental. We are a podcast from RNZ. You can find us at rnz.co.nz/chemistry. You can also subscribe to us as a podcast for free at all the usual places: Apple Podcasts, Spotify, Stitcher and Radio Public.
And if you're enjoying Elemental, then please tell your friends about us. And if you can rate and review us on your podcast app, then please do. It really helps other people to find us. Next time on Elemental, we're looking at arsenic. And until then, it's bye from me, Allan Blackman from Auckland University of Technology.
And from me, Alison Balance. Catch you next time. Mā te wā.